Okay, let's get started. Who'd like to offer a prayer for us? Go ahead. Ashlyn, right? Thanks, Ashlyn.
Dear Heavenly Father, we're so grateful for the opportunity to come to class today and to learn from Brother Corey. And please bless that we might understand and have the Spirit with us to enlighten our minds and to remember what we learned this day. And we pray these things in the name of Jesus Christ. Amen.
Amen. Hey, thank you. All right, there were a few new ideas. Well, before we do that, devotional tomorrow, it's a member of the presiding Bishop Brick, Bishop Budge. So please be sure to listen to devotional. A few new ideas in this section. We're going to start getting into lots of new ideas. You're going to have so many new words and ideas to remember. Start writing them down and reviewing them frequently. And one of the reasons is that when we start thinking about matrix multiplication and kind of solving systems of equations, there's 5 or 6 different ways to make sense of what is happening. And all of them are advantageous in different situations and to help us understand different things. And so we'll be doing the same thing and we'll be applying different language to it, different words and different ideas to it. So we have a whole bunch of new ideas coming out. So just a forewarning. And then we'll be making connections between all of those different ways of seeing matrices and systems of equations. Okay, go ahead and quickly talk to your neighbor about questions you may have had on this section or things that were confusing on the first part of 2.3. And then I will ask for questions. And if you want to blame your question on your neighbor, go ahead. So go ahead. All right, let's get some questions out here. What are some questions you guys talked about or you heard that people were confused about or hard to understand things? Anyone? Yes, Cambria.
In the video, you talked about like spans of linear dependent versus linear independent, and you had like the example of U, V, and W. And I just didn't remember which one was the one where it would do U to V, and then the one where it would do U to V to W.
Oh, dang.
I just like
I made that, I didn't go back and rewatch the video. I made it last semester and I don't have it fresh on my mind. So,
I just didn't remember like which one you would go to like all three and why.
like which ones you would need all three for?
Yeah, for the span.
Okay, all right, we will talk a lot about spans today. So if by the end we haven't answered that question, come catch me after class. We won't focus as much on linear independence and dependence today. So I don't know if we'll get to that, but come catch me after class and we'll talk about it. Yeah, so spans of sets, it's gonna be a big theme. Okay, other questions? One question I heard was, in WebAssign, it's confusing about which way do you put the vectors. Right now, we almost will always work with vertical vectors, okay, column vectors. So you're going to put in your values this way, okay, not that way. So it's, yeah, the way we build it up, it's a lot easier to think about linear combinations of columns. So that was, yeah, one question I heard. Other questions we want to be sure to hit as we go through today? Okay. Please don't hesitate to ask if we get to something that's not clear. Okay. So here's the problem. Let me give you a few minutes to keep working on this problem and thinking about this problem, and then we'll come together as a class. We'll use 2 servings of bread for a peanut butter and jam sandwich. So 2 pieces of bread, 1 serving of peanut butter, 1 serving of jam. Which one? This is supposed to be 34. Oh, sorry. This right here, that's not the answer to the first one. Yeah, yeah. Oops. Okay, let's talk about these. Okay, so how are we going to answer number one? Hopefully this was pretty straightforward. Someone raise your hand. Yes. So 16.5, so you probably use one serving of bread. Okay, so she used one serving of bread, one peanut butter, and jam. That's great. Oh, wait. No. Here you said, so how much did you get for the fat with in this number one? You said 16.5? Oh, yeah, okay. Yeah, so so some of you may have used one or two. It doesn't matter as much. Just practicing like, hey, can you take one of these to, some of each of these, we're going to add them together and combine. That's the idea of linear combinations, okay? So whether you use 2 or 1 pieces of bread, doesn't matter. Okay, so I lost my screen here. There, okay. Can the number of servings of bread, peanut butter, and jam be adjusted in my diet to get me to a goal of 12 grams of fat, 2.5 grams of protein, 34 grams of carbs? Okay, I row reduced here for you, so you don't have to do it. So someone raise their hand and explain what this means when we row reduce. How does it answer my question here? Yeah, Sydney. Okay, yeah, so if you put into a matrix like this, you row reduce, and we can think about it this way. What we get at the end, you can pull the, thanks. What we get at the end is we get P, the number of servings of peanut butter that we need. Did I eat a bread? Oh, number of servings of bread that we need is a -2. So I need to eat 2 fewer slices of bread in my diet. I need to, what's the next one? Peanut butter. I need to increase my peanut butter by 1 serving, and I need to increase my servings of jam by 5 servings. Okay, so it tells me how many servings of each. Now, the one way to think about this, so coming back to the board here, so these are 4 different ways to write the same thing. Okay, the one over here on the right, this is how we're going to write it next chapter. Okay, so this is a little bit, because we haven't talked about matrix vector multiplication yet. I have in the peanut butter book, so hopefully you've seen it, and I know a lot of you have seen it other places. Here's the system of equation way. Okay, here's the augmented matrix way, where we would drop a lot of stuff to make it easier to do computations with. But we can write it this way. This shows the linear combinations of the vectors. Okay, I'm getting B amounts of this vector, P amounts of this vector, J amounts of this vector, and I want this. So I'm trying to figure out, what are my PB and Js? How am I going to scale each of those? What amounts am I going to take each of those to get that? Okay. Starting next chapter, we'll write it like this, where PB and J will be a vector. And then this is the exact same thing as this. But you don't have to know that, right? Or you know it, but you don't have to understand why right now. Questions about these 3 representations? Okay. I mean, hopefully you can see that, like, just factoring out the p's and writing these as vectors gets you to this. So, okay. So the idea of linear here, let's go back to that last question. So it is possible, we found the number of servings. Is there any dietary goal with fat, protein, and carbs that I could not reach with bread, peanut butter, and jam? Why or why not? What do you guys think? Yes. Okay, so for those online, what's your name? Ethan said he's guessing that there's not. Okay, why would you guess that there's not? Okay, so you said none of the vectors are parallel to each other, so so it should span all of R3. You're thinking, hey, each of these is a pivot column, and so I should be able to span 3 dimensions, and since I'm in R3, I should be able to get to anything. Very nice. Okay. Other thoughts people have? Yes. All right. Okay. All right. So that comment was about I probably shouldn't try to get every goal here because some of them could kill me over time, or if I ate too much of one in one sitting, I might die too. So, and physically, I can only eat so much. And you know, what does it mean I'm not eating 100 servings of bread today, right now. So what does it mean to drop 100 servings, to take 100 servings out of my diet? So there are some physical things. Okay, nice. So the book does an example where they do a proof to show that 2 or 3 columns will span R2 or R3. And they put like XY or X, Y, and Z over here. And then they do some row reduction, and they end up with formulas over here in terms of X, Y, and Z. And that is one way we can prove things. You can do that, and then each of these would tell you, oh, if you give me a goal, if you give me a point in terms of X, Y, and Z, you give me your favorite point in R3, then the formulas we come up with over here, we can plug in and we'll know exactly, that'll tell me how many servings of the first, how many servings of the second, how many servings of the third I need to get exactly that value. One of your homework problems is like that, okay? We're not going to take time. I don't think we'll have time to do it today, although we have one if we do have time. But it's pretty clumsy, and we'd like better ways to think about what's going on. Okay, so we're going to build a little theory here. Okay, get some powerful theorems, so we don't have to do that like every single time. Okay. So it turns out it is possible, and we're going to connect it to this idea of pivot columns and what we wind up calling dependent or independent vectors. Okay. So you can think about linear combinations just quickly as the easiest kind of recipe. We're going to just take some of each and throw them together. So take some of each means we're scaling each of the vectors. Combining them is adding them up. You don't have to combine 2 certain things first and then add something else over here and then combine those. Doesn't matter. We're just kind of putting all of these together at once. So you can think about the peanut butter and jelly sandwich this way. We already kind of emphasized that here on the board, that you can take the 1 peanut butter, one serving of jam, 2 slices of bread, and you'll get this. When we think about linear combinations, this is usually the notation that we use. So CI for the constants, that's kind of like the servings that we take. VI for the vectors. So we have so much of C1 of V1, C2 of V2, C3 of V3, etc. And we add all those up. Okay, any questions on linear combinations? There are certainly other ways of doing combinations, but in this class we're focusing on linear combinations. That's hard enough to understand. So, okay. the big questions that we're leading up to and working on is, when is one vector a combination of other vectors? The problem I just gave you about the fat, protein, and carbs is that kind of question. Hey, I've got peanut butter, jam, and bread. With their vectors, can I get this goal? So this is one where system of equations is really nice, especially if we just have one individual vector we're trying to reach. But if we want to know about infinitely many vectors, so for example, what are all of the vectors? What are all the possible dietary goals I could reach with these 3 foods? We're not going to take the time of writing each one of those out and then doing real operations to see if we can find it. We need something else. And this is where span comes in. The span of a set of vectors lets us know all possible vectors we could get to with a combination of a given set of vectors. The other big question we're building up is, if we can't get there, if it's not a linear combination, what's the closest we can get? So later in the semester, we'll be using projections. A projection onto a span of a set of vectors is the closest we can get. And those are, in practice, we actually end up doing this a lot more than this. This is extremely valuable, and you use this stuff all the time, or the stuff you use uses this stuff all the time, like compressing pictures and compressing audio into MP3s. That's the kind of stuff that's happening there. Okay, one quick example, because where you have dealt with spans before. Any color can be made up of a combination of cyan, yellow, and magenta. You can take linear combinations and make any other color. So the span of those 3 is like all visible colors, okay? There are different ways, side note, there are different ways to do this. Red, green, and blue is what screens use, because your eyes have red, green, they pick up red, green, and blue light. And so to make it a better fit for your eyes, they use red, green, and blue pixels, or combinations on the screens. Hue Saturation Lightness is a new one I learned this semester that you can use. So that they span the color spectrum means that any color you pick can be made with some linear combination of those 3. Okay. All right. So this is a question off of a previous midterm. So I have a few of these we're going to practice on. The question is, which of the following sets of vectors spans all of Rn for the appropriate n? And the first question I'm going to ask, I'm going to just have you talk to your neighbor really fast, is on this first one, what is n? Is n 2 because there's 2 entries, or is n 3 because there's 3 vectors? So just talk to your neighbor. What do you guys think? Just take 30 seconds.
Because if you think about like a system of equations, then it would be 2 equations, 3 variables. So. But also, I remember there being an example of like
All right. Okay, we're just going to do a quick survey. Just hold up 2 if you think it's R2. If we're trying to span R2 here, hold up 3 if the n is 3. We're trying to span R3. So 2, 3, 2, 3, 2, 3, 2, 3. Okay, some of both. More. Hey, we shouldn't have any single fingers pointing at me. All right. Okay, just kidding. No one's doing 1. Thank goodness. Although in some countries 2 is as bad as 1. So in New Zealand, where I serve my mission, we got 2 fingers a lot. Okay, mostly 2. Okay, so 2 is the right answer here, but we want to understand why. Um, so we're trying to span Rn. If you were to take this as a point or a vector, what would you plot it on? Do you need a three-dimensional space to plot this vector? No, you only need a two-dimensional space. This lives in R2. Okay, you just need a plane with two dimensions. So there are three vectors here that live in two-dimensional space. So R2, so n equals 2 in this case. So the question is, do these three vectors, do they span R2? So here, the question is, we're trying to span R3. You need a three-dimensional space to plot any of these vectors. Even if we just had one, you'd still need a three-dimensional space just to plot that one vector. So we're living in R3. So the question is, do we have enough information there that with combinations of those vectors, we could get to any point in R3? So that's another way to interpret this question. Okay. All right, questions for me so far? Yes, Ethan. Oh. Yeah, okay, that's great. So just for those online that didn't hear, Ethan said, what if we added onto the bottom and we just put 0 there? So we have a 1, 2, 0, 3, 4, 0, 5, 6, 0. Then is that still R2 or is it R3? It would be R3 because you'd need a three-dimensional space to think about that, but they would only end up spanning a two-dimensional space, okay? So, but, and they wouldn't span all of R3, where we would find out, but yeah, that's what we're working on now, is like knowing if it would or not. But since all of those Z components are 0, there's no combination you could get to and get like a 1 of Z, right? So you know you can't get to all possible points, because anything that had a 1 as a Z, you're in trouble. So, okay, so I'm going to turn you loose on this, work with the neighbor, try to figure out how you would reason through whether these, whether the spans of these would be all of Rn, where Rn is the number of entries in each of these, in each of the vectors. So R2, R3, R2, R3. Okay? All right, go ahead, take 5 minutes or so. All right. Let's come together and let's just talk about this first one. What are someone's thoughts on the first one? So we have these three vectors in R2. Do they span R2? Like together, can I take linear combinations of those and get to any point in R2? So I see some thumbs up. Anyone want to give an explanation about why they think that it would span R2? Or how we could figure out if they actually did? Yes?
I'm pretty sure that we have more than enough information to span the R2 plane. You could use the first two just because they're not linear, or they're not parallel, or like deal with each other.
Okay, you said we actually should have enough information in just these first two. You said because they're not parallel to each other. Okay. Yeah, so if you have two vectors, it's easy to find out if these two vectors are linear, if one of the vectors is a linear combination of the other one. Because there's only one way you can do it. Is 3, 4 a linear combination of 1, 2? Well, that means the only combination I can do here is scale this. I have nothing else to add. So can I scale 1, 2 and get 3, 4? No, because if I did, I'd have to multiply this one by 3 to get 3. The only thing I could multiply this one by to get that. And then this would go to 6. And so it's not the same. Or if I scaled this one by 2, I could match the 4, but this one would only be 2. It doesn't match. So these are, in the language that we'll talk about next time, these are independent vectors. They don't lie on the same line. They're not parallel. Okay? And you said that's enough for us. Yep. So another way to see that is we could row reduce. You can row reduce this. Even without an augmented matrix, you can start row reducing, or oftentimes we'll actually augment it with, we'll do the homogeneous system, or we'll just augment it with 0. But you can just row reduce. You don't have to do this. You can if you want. If you start row reducing and you get that both of these are pivot columns, then you would span R2. So we could quickly row reduce. If I multiply this -1, this first row by a -2 and add, then I'd have 1, 3, and this would become 0. This would become a -6 plus 4 is a -2. That's as far as I need to go, because now I have two pivot positions. Okay, so I have two pieces of information here, right? We talked about rank. This is a rank 2 matrix. That's the number of pieces of information that we have here. And so we would have enough to span 2 dimensions with these. I don't know, I think, is it Riley? Yeah, I think Riley had his hand up first, and then we'll go. Yes. Ooh, great question. Yes, 1, 2, 3, 4, 5, 6. You absolutely can. Is that your question too? Okay. So yeah, multiply by a -2 and add. And here we'd get 0, a -2. We multiply this by a -10. I'm sorry, by a -2. That would be a -10. Add the 6, a -4. And yeah, we still have the pivot position right here and right here. And this, if we were doing a system of equations and had something else over there, we would have a free variable here, which means we have too much information. And since we'd have a combination here, like we could have something for x and something for y, we could get any point. There's some combination that would get us any point in R2. And since we have the free variable, there's infinitely many ways, infinitely many combinations we could use to get to any point you throw at me. So, okay, yes.
So my question is the number of pivot columns you have, is it safe to say that that's the like already end value that you can span with that pivot matrix?
Yes. So that question was, is it safe to say that the number of pivot columns that you have, that's the what did you say, the dimension that you span? Yeah, the Rn that you span. Okay, so not Rn. It's not the Rn you can span, but it's the dimension that you can span. So, so since I have 2 pivot columns here, I can span 2 dimensions. Since these live in R2, that's everything. But if I row reduce, you want to pull up the, Michelle, can you pull up the problem set? Okay, like on that third one, if we have 1, 1, 1, 2, 4, a minus 2, 0, 0, 0. When I row reduce this, what's the highest the rank can be, or what's the highest number of pivot columns I could have? 2. This could never have, this couldn't be a pivot column, right? So I could span 2 dimensions, but I live in, these live in R3. So I've got 2 vectors in 3 space, and the combination of those will stay in a plane that slices through the 3 space, slices through R3. So I can't get everything. So, but here, let's actually do some row reduction here. So I multiply by a minus 1 and add here. I get 1, 2, 0, 2, and then I can do a negative 1 here and add, and I get 0, a negative 4, 0. So I can then turn that to a 0 with this one. I've got 2 pivot columns. So this would span, so it would span a 2-dimensional subspace, like a 2-dimensional slice of R3. Okay, yes? That's it. Yeah, Michelle, can you go back to the problems?
So the variables in each of those, say on like number 3, it'd be x, y, and z going down. Usually when we put it in a matrix, the other ones we write it as x, y, and z. We have to rewrite it like that.
So that question is, if we wrote this as a system, we would have x plus 2y plus 0z equals, we don't have a particular answer.
So why would it be x, y, and, or what, how come it's, because in the first vector it's like 1x, 1y, 1z, like when it's written as individual vectors?
So these, yeah, so for those online, he said, well, wouldn't we think of this as 1x, 1y, 1z? Yeah, so the xyz, this xyz is something different than the xyz here. Okay, so yeah, this can be confusing. So if we're thinking about coordinates, then the coordinates of this vector is 1x, 1 in the x direction, 1 in the y direction, 1 in the z direction. Okay. If we're thinking about, we could also think about linear combinations where we're just using x, y, and z as unknowns, and if we're trying to say, let's go back over here. We're using B, P, and J as unknowns, and how much of each do I take here? Then that's different than each of these coordinates, because these coordinates are in a different space. In this context, we have fat, protein, and carbs. Yeah, so this is fat, protein, and carbs. We're in a fat, protein, and carb space with each of these. But the combination of these are representing unknowns. Those unknown values are how much bread, how much peanut butter, and how much jam. And sometimes we'll use mathematicians like x, y, and z. And so it can be confusing because sometimes they'll talk about x, y, z just in general with the coordinates, but then they'll also sometimes write x, y, and z to be the unknowns here. So yeah, that can be confusing. So okay, other questions? Yes.
So when the one we just did, like the third one there, the 1, 1, 1, that one, there's 2 pivot points.
Yep. There's.
So it can span 2 dimensions. If you think of it as
We're not going to think about it that way yet. You could say that we could do a transformation or kind of a mapping and connect all the points in R2 to all of the points that this spans, but that's a little more advanced than we're at right now. Like basically the dimension is the same. You could translate one into the other, but we're not going to say these span R2 because these, yeah, these live in R3 right now. So nice question, nice question. Okay, other questions? Yes.
We were talking about why two parallel vectors or like vectors that lie within them, why they can't span. Can you explain that a little bit more and like mathematically how would you use that?
Oh, beautiful question. So they said, why do two vectors? So there is an example here in this problem. 1, 2, and 2, 4. You've got two vectors here. They're not the same vector. They're different vectors, but they lie in the same line. 1, 2. So 1, 2, right there, and then 2, 4, right there. Okay. So why can the first question was why can they not span R2? No matter what combination I take here, maybe 5 of the first and maybe a -2 of the second. No matter what I get, so here I get 5, 10, here I get a -4, a -8. So what does that end up with? Did I just end up with 1, 2 again? Yeah, because this is twice as much as this one, so that's like 5 1 2s minus 4 1 2s. I get 1 2. You can only, yeah, everything I get, no matter how I change these values, I will get a combination of just a scale of a scaled version of 1 2. So it will only live on this line. Like this? Yeah, so these two vectors, they are the exact same vector. They're just written in, they're just drawn in a different, they just start at a different point. But this is still be the vector 2, 4. This is the vector 2, 4 starting at the origin. So yeah, so these are the, no matter where I draw that 2, 4, that 2, 4 is the same. So yeah, so the easiest way to make sense of it right now is, yeah, we're going to start the origin. Can I get to everywhere? And you can't, no matter what combination you get. You can do some algebra and show, like, you're just going to get some multiple of 1, 2. So, and the second part of that question was, how do you show it by row reducing? Well, what if we row reduce this? Take a -1 of this first row, add it to the second row. I get 0, 0. So I only have one pivot position there. So I only span a one-dimensional space. I really only have one piece of information. Great question. These are really good questions. I hope they're helping you guys. Other questions? Okay. Michelle, can you pull up those problems again? Let's look at the last one. So, yeah, so we can go through these really quick. Yes, this is enough information. That turns out to be more than enough. Yes, exactly the right amount of information. Not enough information. 0, 0, 0 doesn't help you at all. You really just have two. We row reduced, and we just found we have two pieces of information there, two independent vectors. Not enough, because these live on the same line. We just talked about that. Not enough, because you just have one vector. You can only scale it in terms of linear combination, so you just get the one line, same line as you get there. What about this last one? Go ahead.
I said it does span R3.
Why do you say it spans R3?
Well, I didn't row reduce or I guess it kind of already is, but I just figured like the 1, 1, 1 vector, you just multiply that by whatever scalar you want to get the x value to be correct. And then you add the second vector.
Here, hold on, let me give you this. Flip. Shouldn't have my jacket. Okay, go ahead.
All right, so the 1, 1, 1 vector, you just multiply it by whatever scalar you want to get it to be whatever arbitrary x value, like for the first component. Then you multiply this, like you add a scalar multiple of the second vector to get the y value to be whatever you want. And it won't affect the x value that you originally had because that's 0. And then you just finish it off by like adding a scalar multiple of the last vector so that your z value is whatever you want. So any like x, y, z in R3 will be able to be reached by those 3 vectors.
Very nice. Very nice. Did you guys catch that? Okay. I don't know if everyone caught that, but sorry, got a PhD and I can't run a mic clip. Okay. He had a way to reason that each of these, because of these zeros here, if you give me an x, maybe -10, I can just multiply this by a negative, the first one by a -10 to get the x coordinate that I want. And my y coordinate, well, I'm at a -10 right now, but if my coordinate is 0, I could multiply this second one by a -2.5. No, by 2.5. I would cancel out my -10 that I already had to get my 0. And then I'd have whatever I'd get down here. I can't remember what I had right now. But then I could adjust this last one to compensate and get my third coordinate. So he had a way to reason through like why you should always be able to get that last coordinate. So we can row reduce. We could also reason that if you just rewrote it as 0, 0, 7, if you rewrote the set this way, well, Michelle, now I don't know what it was. One of them was 1, 1, 1. 1, 1, 1.
I put it back up for you, sorry.
Thanks. 0, 4, 2. So if you rewrite it this way, and we put it into a system, thinking of it as a system of equations, then what row reduction could we do? You could just swap the top and the bottom rows, and you would have 7, 0, 0, 2, 4, 0, 1, 1, 1, and then it's already in. Now it is in row reduced form, not reduced to row echelon form. It's in row echelon form. We have 3 pivot points. So you guys already, some of you already saw, hey, we already had three pivot points, except that the zeros were in a different triangle. It still works to find pivot positions. So we have enough information there because of those pivot positions. That's enough to know that if you put any set of coordinates here and continue row reducing, you get a 1, 1, 1, and that's enough to know that you'd know what x equals and y, how many of these you'd need, how many of these you'd need, how many of these you'd need. All right, thank you very much. Have a great day. I hope this was helpful. Homework's up on the board over here on the right.